So recall the counting formula. So the counting formula tells us that if G is a group and H and G is a subgroup, that the order of H times the index of G and H, that is the number of cosets, is equal to the order of G. And we derived this just from the axioms for what a group is, what a subgroup is, and what what equivalence relations and partitions are. Okay, so now we want to apply this counting formula. So let's start with Lagrange's theorem, which is just going to be the simplest possible way we could apply this formula. This is Lagrange's theorem. Lagrange's theorem says that H, so let's just, G is a finite group. Again, H is a subgroup of G. And this says that, so maybe I should, this is a hypothesis, I'll move it up here. H is a subgroup of G, then the order of H divides the order of G. Okay, this is, and I'm not even going to prove this. This is pretty clear from this formula. You just, you have this equation. The order of H times another number is the order of G, so therefore it must divide the order of G. Let's take this even further to this corollary, which is often also called Lagrange's theorem. And this corollary is the order of any element, any G in G, divides the order, the number of elements in G. So that's, and the proof of this is just apply the theorem to H equals the subgroup generated by our element. Now this is kind of interesting. We're starting to get, so we just started out with the axioms of groups, right? We proved this formula, and now we say that any element, its order has to divide the order of the group G. So somehow there's some, and this is for G a finite group, but somehow there's some divisibility that's going on, some divisibility properties. And what's even more interesting, at least if you ask me, the corollary, which is let G be a group of order P, where P is a prime. Then G is cyclic. Okay, and the proof of this is, well, we used the previous theorem, well, really the previous corollary, and that tells us that, for any element, So let's say any G in G has the order of G equals, well, it has to equal something that divides P, so it's equals 1, or it equals P. And if the order equals 1, then that means that G equals 1. So if this is going to be a non-trivial group, then the order of G has got to be equal to P, as long as G is a non-trivial element. So but the order of G is equal to P, and P is already the order of G, that means that equals P for some G, and this is exactly what it means to be cyclic, because that means every element in the group is going to be a power of this particular element. So that means that G is cyclic. So the point is that this counting formula and Lagrange's theorem, or this, other version of Lagrange's theorem, they tell me some very, very strong things about what the elements in my group can be doing. And if, for example, the order of my group is prime, there's nothing else that they can be doing other than having prime order, because the order of an element divides the order of a group. The order of the element divides the order of the group. So now, just from this formula, I can tell you every single group that has prime order. They're all cyclic. And I think this is kind of an amazing theorem, considering the fact that we got it all just from those three axioms of what it means to be a group.